Today's lecture concerns the diffraction of light. Diffraction, it laughs in the face of ray optics because diffraction is all about telling ray optics that light is not going to go along the direction that the ray says it should. We'll have a look at how diffraction is similar to interference. We'll look at there are two basic types of diffraction, Fresnel and Fraunhofer. And we'll look at how Fraunhofer diffraction can actually be easily explained in terms of Fourier analysis. We'll use that to simplify the analysis of diffraction later in the discussion. We'll look at simple systems, a single slit, a double slit, and then gratings, which are made of many slits. We'll look at how these gratings can be used in spectrometers. In the classical picture, if we have a wavefront coming along and we want to know what is the electric field at some distant point, what we do is consider that every point on that wavefront is the source of a secondary wavelet, and those secondary wavelets are spherical. This is known as the Huygens-Fresnel principle. So these wavelets will expand and they will superimpose at that point there. That will be how we calculate our electric field. Spherical waves also expand in all directions. So we really will need to consider this wide range of angles when we are looking at the electric field at various positions. These secondary wavelets also have exactly the same wavelength, frequency, and were created at exactly the same time because they're from that same wavefront. So they're coherent. We know from our lecture in interference that when we have the superposition of a number of coherent waves, we can see really interesting interference effects. The interference effects are, of course, seen when we look at the irradiance. And when we are looking for interference effects, it's path length changes and phase shifts that we are looking for. If we look at these two examples, one of interference where we have light coming into a thin film reflecting off two surfaces and recombining, and we compare that to diffraction where we have, for example, X-rays coming in and they are reflecting off rows of atoms. You can see from their equations that actually pretty much the same thing is going on. The difference of the cos compared to the sine is simply because we have a phase change at the reflection from the high N surface. So physically, there's no real difference between interference and diffraction. What we will tend to do, though, is talk about interference when we're only considering superposition of just a few waves. And we'll talk about diffraction when we're also emphasizing that the ray picture is not applying and we need to consider the way that the wavelets are actually spreading out. Let's return to our Huygens-Fresnel principle. When we have a usual plane wavefront, it extends infinitely in all directions in the plane. So that means that for every wavelet that is expanding in a certain direction, there is going to be another wavelet that is expanding in an opposite direction, and that means that they will always cancel in directions theta's other than straightforward 0 degrees. So we'll have a new wavefront which is formed in front, and we'll have our normal plane wave propagation the way that we're so familiar with. But when we then block our wavefront, remember we will only have these wavelets coming from the unobstructed part of the wavefront. Now you can see that wavelets that, for example, are coming from just the very edges of this wavefront will be expanding in all directions, and there's going to be a situation now where we no longer have wavelets out at infinity that can cancel out. So this lack of cancellation is going to give us the most interesting effects. Now let's look at Young's famous double slit experiment. First of all, we have two slits. The slit width is actually approaching 0. The slit length is infinite. The length of these slits runs in and out of the plane of the screen you're looking at right now. Young's double slit is often given as an example to teach people interference. However, there's an important part of that picture which is sometimes missing. And that is, we have light coming towards two apertures. Why isn't it that we simply don't see light going through those apertures and we just see two bright spots on the other side? Why should light even exist in between? To explain this, we need to use our Huygens Fresnel principle again. That says that each of these small slits is going to act like a stack of spherical wavelets. So we can also consider our secondary wavelets then to be cylindrical waves. That's just the sum of a stack of spheres. So the fact that we can now consider cylindrical waves now gives us a reason to expect that we can have electric fields both in between the points where geometric optics would explain our light would be, and in fact everywhere else. So between the slits here you can see that the electric field shows that there is an interference going on. The electric field strength here is indicated by colors, where white is the most intense and black is the least intense. Behind the slits, well, nothing's going on. We've just got a plane wave arriving at an absorbing screen. Near the slits and far from the slits, well, we have interference going on in both places. But when we are far from the slits, such as up here, you can see that our cylindrical wavefronts are now almost planar. Whereas if we are very close into the slits, then they are most definitely cylindrical. And we can consider that these are two regions where we can use different approximations for the patterns that we'll be forming. Far from the slits, we're going to consider patterns that are called the Fraunhofer patterns, and near the slits we're going to be looking at Fresnel diffraction. Let's have a look at our picture a little more quantitatively. In this case, we can see that there are about 5 wavelengths between the two slits, and that is because each of these wavefronts is, of course, 1 wavelength apart. So how many fringes are there? Well, it looks like the fringe spacing is about half a wavelength. However, we can only see, I would say, about 8 fringes, not 10. It's hard to tell because the contrast is really decreasing as we get closer to those points of light. Now, the reason the contrast varies, let's change color and let's consider a point here that's very close to 1 but quite far from the other slit. Now, we know that the electric field in a spherical wave is going to decrease as 1 over r. So that means that the electric field due to one slit is going to be much, much less than the electric field due to the other slit. And from what we saw in interference last week, if we want to have a high visibility or high contrast pattern, actually we want to have E1 of the order of E2. So that's why the contrast has gone down and we don't see those fringes near the slits very well. Fresnel diffraction is also known as near-field diffraction. We need to take into account Fresnel diffraction when we are at a distance that is much, much less than the size of the object, in this case the distance between the two slits, squared divided by the wavelength of light. When we are in this near-field region, which I'm indicating here with blue, then we need to take into account the spherical wave nature of the light that's coming from the aperture. And that gives us rather difficult calculations to do when we need to work out the superposition. And we need to do this because in this near-field region, there we have very curved waves, we have different strengths because at any given position you're going to be closer to one slit than the other, and you also need to take into account the different angle. So it is not easy to do, and I would in general suggest that you want a Fresnel diffraction pattern, you get a computer to solve it for you. Although the calculation may be tricky, Fresnel diffraction has some really great applications. One example is X-ray lenses. A difficulty with focusing X-rays comes about because the refractive index of most materials in the X-ray region is about 1. So it's really hard to make a mirror and even harder to make a refracting lens. So how do we focus X-rays? One thing that we can do is use a zone plate, and the zone plate uses diffraction to focus X-rays. Let's have a look at an example down in the bottom right. We have a point source of electromagnetic radiation, let's say it's X-rays in this case. And I've indicated in red and blue wavefronts that are pi out of phase with each other. So we'll call the red ones in phase and the blue ones out of phase. You can see that the design of this zone plate, which is a series of apertures, it's been made so that at every opening the light is exactly in phase. So all of our secondary wavelets in the plane of this aperture are in phase. And when we have a whole bunch of wavelets in a plane that are in phase, then of course their wavelets add to give us plane waves. So from what you can recall perhaps from all of our geometrical optics, we described a system where we had plane waves or an image distance of infinity on one side as giving us an object distance of the focal length on the other side. So this completely flat thing is effectively a lens. The example on the left-hand side shows plane parallel light coming in other words, the object distance is infinity, and you can see that it is focused. In this instance, you can see that there's a real brightness and increase in irradiance on axis, a distance one focal length away. It's not exactly the same as our regular lenses. You can see there are some additional weaker foci at other distances from our lens, but nevertheless it's still pretty good. And it is a simple matter to calculate the radius of each ring, starting from the center and counting out 1, 2, 3, and so forth to each boundary. And it of course depends on the focal length that you want to have and the wavelength of electromagnetic radiation. In this straightforward example, you'll work out the radius of the central zone of the zone plate. So here is the wavelength of your X-rays, and here's the focal length you need to work with. Fraunhofer diffraction is also known as far-field diffraction. It's what we see when we're far enough away from our diffracting object so that r is greater than d squared, where d is the largest size or diameter of the object or obstacle that we're looking at, divided by the wavelength. When we are at a position that's quite far from our diffracting object, the waves are going to be nearly flat, so they are planar wavefronts that we are seeing. The waves from each of the slits is going to will have a similar electric field strength, and the wave from each of the slits is going to be traveling in a similar direction. So these are going to be roughly parallel. So our summing is going to be quite simple. Our superposition principle that we will use in order to calculate the electric field is going to be the sum of plane waves, in fact plane waves of equal intensity and traveling in the same direction. As a quick aside, the electric field goes as e to the I k wave vector dot r position vector minus omega t, which if I expand out this becomes e to the I kxx plus kyy minus omega t, where I have pulled out the k vector into its components, kx and ky. So that is where this term is come from, why I want you to see that the electric field is proportional to e to the I ky. And the reason I want you to notice that is because when we're working out the electric field, we are summing these terms. And if you didn't already get the hint when I said we're going to be summing plane waves, I hope that you get the hint when I say we're going to be summing these e to the I ky terms. What we are doing is a Fourier series. With diffraction, as with interference, we're often most concerned with the irradiance pattern. And we know that the irradiance pattern is going to be bright or dark, depending if we have constructive or destructive interference. So constructive interference will occur when our path difference is 0, 1 wavelength, 2 wavelength, so forth, and the destructive interference when we have some integer multiple of half wavelengths as our path difference. So path difference is going to be something that we'll be emphasizing. In the example on the left-hand side, I'm working out the electric field here at position X and position Y is equal to 0. You can see that the electric field and the irradiance at that point there is going to come from two plane waves which have a path difference that they've travelled of exactly 0. So they're in phase and we have constructive interference. Now if I then move up the y-axis to here, and if I move such a distance that one of the plane waves has now travelled an extra wavelength, then of course they are in phase again and we also get constructive interference. So let's have a look at the path difference between our two plane waves at a large r. We're going to consider the electric field at a point P at some arbitrary point xy. So r1, the distance from slit number 1 to the point of interest, we can work out that distance using Pythagoras, and then we can do a series of approximations such as dropping this very small d squared on 4 term. Then we've factored out x squared plus y squared, which is equal to r squared there, and then we use a series approximation, which is something we've done in previous lectures before, to end up with this approximate expression for r1. We then find our difference between R2 and R1, which gives us this path length difference here. And we have Y on R. As you can see here, there's Y, there's R, is going to be equal to sine of theta, which is the substitution in here. So this expression gives us a way of determining what the path difference is as a function of angle as we travel around. Now let's see if we can calculate what the amplitude of the electric field will be at some position xy, just as we did for interference last week. So we are going to be summing our plane waves because we are far away, and the electric field at this point here is going to be proportional to the e to the I k r1 plus e to the I k r2. That's our superposition principle in action right there. In the previous slide, we saw that we could use these terms here as approximate expressions for R1 and R2. Then what I've done is I have factored out this e to the I kr, and I have put it as a constant of proportionality. Now you might say, well, it's not constant, right? Because we're going to vary y. And isn't r a function of y? Well, yeah, it is. R is a function of y. It's equal to x squared plus y squared, the square root of all of that. But y squared is very, very much smaller than x squared, okay, because we're viewing a long way away. So we could write this as a series That would be square root x squared plus y squared 2 square root x squared plus some other terms. And you can see that this is going to vary very, very slowly with y squared. R of y is practically a constant. So it means that this term is not going to rotate around very much as y changes. It'll barely move at all. So that's why we're considering a constant. And then we have done some substitutions for angles and ratios of sides as we have done before, and we've used Euler's theorem as well to re-express it as the more easily visualized cosine. So our intensity pattern then is going to be a squared cosine. And as we saw before, remember we came up with a path difference of d sine theta. If we want to turn the path difference into a phase difference, we just multiply that by k. We will see fringes every time that phase difference is equal to an integer multiple of 2 pi m. So this is the expression here that we can use to find out where the fringes are located, the bright fringes. We're going to describe mathematically our slits as a function. So we have a feature, a slit at d on 2 and another one at minus d on 2. They're infinitesimally thin and infinitely long, so a Dirac delta function is just the thing to describe them. And the expression that I've written here is the aperture function, which is the sum of those two delta functions. If you're really keen, then you might have noticed that these delta functions and this electric field are actually a Fourier pair. I can make it even clearer by rewriting this k sine theta as ky. Ky is simply the y component of the wave vector. So what we've shown, and you can more formally do it too, is that the electric field at some distant place is a function of ky, and that's going to be equal to the Fourier transform of the aperture function. So it's rather cool. The Fraunhofer diffraction pattern of some kind of object is actually the Fourier transform of the object. This is great news because when we worked out the pattern from Young's double slit, we had to do an integration. Well, in this case, we just had to sum two waves, and that's not too onerous. However, once we start getting to apertures that are, well, not infinitesimally thin, we will have to do integration, and that's a pain in the neck. Far more easy to simply take a Fourier transform. Now we're going to consider diffraction from a single slit. It's still going to be infinitely long in the z direction. However, now in the y direction, it's got a finite width of a. When we consider single slit diffraction first, either in year 12 or in first year, usually what we do is we just take the rays that come from either edge of the slit, and we look at the interference between them at some screen a distance d away. And that's quite nice. It certainly explains the locations of the maxima and the minima in the pattern. So a lot of the basic physics is actually captured because we can see that with this model that if we have a wider slit, then we're going to have smaller angles between those maxima and minima, whereas if we have a narrow slit, then the angles are going to be larger. However, if we want to actually do this properly, we need to consider that not only are waves coming from the edges of those, the aperture barrier, but wavelets are also coming from everywhere else within the opening of the aperture. So to work out what the far-field electric field looks like, we need to consider the contributions from all of these wavelets. That means that we need to do an integral, or as we've seen already, the far-field diffraction pattern is a Fourier transform of the aperture. So let's use that approach. So we're going to look at the aperture function that describes our long slit in the z direction, and we're going to take the Fourier transform of that to work out what the far field electric field looks like. So we're going to illuminate with plane wave as usual, so we assume that across the aperture there's no phase variation. And our aperture function looks like a square. So between the values of y is equal to a on 2 and minus a on 2, then it's going to have an amplitude of 1, whereas everywhere else it'll have an amplitude of 0. So now let's take the Fourier transform of that to work out our electric field, which is a function of k. To do that, we multiply our aperture function by e to the I k y, or equivalently I y k sine theta, and then integrate it in the y direction over the aperture. So our aperture only has a finite value between minus a on 2 and a on 2, and a is equal to 1. So this is a fairly straightforward integral to carry out. We arrive down here and we use Euler's theorem to simplify it, and we get this expression for e to the k, our electric field, down here. So this function, sine beta over beta, which is also known as sinc beta, is illustrated over here. You can see it looks like a sine, however, it's got an amplitude that decays, and also at beta is equal to 0, instead of being having a value of 0 as a sine function does, it actually reaches a maximum of 1. But otherwise, the zero crossings occur at the same place as you would expect them to occur for a sine function. If we square this electric field, then we will be able to obtain the function of the irradiance pattern. So as you can see, the irradiance pattern, not only do we know where the zeros of destructive interference occur and the bright constructive interference occur, as we saw before, we now actually are able to talk about the relative irradiance of those different spots. So we know that the central spot is going to be quite wide and the most intense, and we can also see as we get further and further away from that m is equal to 0 order, that the intensity is going to drop off. To avoid even having to do that integral, you can simply look up the fact that our aperture is a rectangle, and the rectangle function is going to take the argument y on a, and we look up the Fourier transform pair with that, which gives us A times sinc of ky A on 2. And the irradiance pattern, of course, is going to be related to the square of that. So we have a sinc squared. As we saw before, we're going to have destructive interference whenever the sine function here goes to 0. So that's going to be whenever beta is equal to pi, 2 pi, and so forth, or an integer multiple of pi. Which, if you want to re-express in terms of wavelength, is this expression here. The important thing is that m is equal to 0 is not a minimum, as I mentioned before. And that is because the sinc function, unlike the sine function, is actually equal to 1 at the when the argument of the sine goes to 0. Now let's consider a rectangular aperture. It's no longer going to be infinite in the z direction, but it's only going to have a finite length b. We'll continue to use the same width in the y direction a. If you want to pursue the integral method of working out the far-field electric field, you need to now consider that your position vector r also needs to include z. However, we are going to stick with the simpler Fourier transform approach. So we now have a two-dimensional aperture function that we need to write, which I've written here on the left. And our Fourier transform then, which is going to give us the electric field, is going to be a double integral now over the z direction and the y direction of the aperture function, which is 1 times e to the I kyy plus kzz dy dz. Unsurprisingly, it gives us here a far-field electric field that's a product of sinc functions times AB, which is the area of the slit. And our irradiance pattern is going to be proportional to the electric field squared, which gives us the product of two sinc squareds functions. Let's have a look at the contour plot showing intensity in the middle. If we look in the y direction, as we were before, you'll see that you have the normal sinc function that is associated with the finite width A. And if we look in the z direction now, we also see a sinc pattern, and that's associated with the finite length B. In other positions, you can see that we've got a sort of a rectangular grid of these dark or destructive interference lines. Now, just to check that we're going to get the same result as we did for an infinitely long slit, what happens when we let B go to infinity? Well, in that case, you can see that B going to infinity means that BZ is going to go to infinity too. And that's going to increase the frequency of these oscillations in the Z direction such that the pattern all squeezes up towards the Z is equal to 0 position. And then that just leaves us with an oscillating pattern in the Y direction as we had before. The two figures down the bottom show you a three-dimensional way of viewing the irradiance pattern. As you can see on the left-hand side, the central maxima is very much larger than those subsidiary maxima, whereas I've used a log plot on the right to show you those that square grid of the maxima a little more clearly. In this problem, you're going to take light with wavelength of 633 nanometers. You're going to put it through a single slit. You're given the width, but not the length of the slit, so let's assume that it's infinite. And it's going to form fringes at a distance of 5 meters away. I need you to find the distance, not the angle, between the central maximum and the first minimum. And then I would like you to do some modeling to confirm this. When we looked at Young's experiment before, we took the slits to have 0 width, and our aperture function was just 2 delta functions. That gave us a far field electric field of a cosine, and the interference pattern that we saw was a cosine squared. Realistically though, each aperture has to have a finite width, for example A, and the real diffraction pattern is never going to be as simple. So to work out our new aperture function, we will convolve our single slit of width A with our 2 delta functions, which gives us a double slit. Now, convolution theorem tells us that if we convolve 2 functions, the Fourier transform of that is simply the product of their respective transforms. And since we already know the transform for a single slit or for 2 delta functions, we can work out then what is going to be the product of their transforms. So single slit diffraction will give us a sinc function. The 2 delta function gives us a cosine. Multiply those two together and we will have our real double slit interference pattern. You'll see that the pattern contains both the rapid oscillation due to our Young's double slit effect of the 2 delta slits, and we also have the slit diffraction effect, which causes this broad envelope over the top. If we square that electric field pattern, it will describe our irradiance pattern, which you can see here. And so it's a very useful general rule that if we convolve aperture functions, for example, then we multiply their diffraction patterns. We're now in a position to extend our picture of the double slit to that of the grating. So now we will consider a grating similar to the double slit as a convolution between a rectangular aperture, we'll call that a slit, convolved with not 2 delta functions, but a whole array of regularly spaced delta functions. We'll call that aperture A delta. That means that our far field electric field is going to be the Fourier transform of our grating aperture, which is then the product of the Fourier transform of the slit and the Fourier transform of the delta functions. So in the graph on the right hand side, you can see we're going to have this broad envelope, which is due to the diffracted field from the second slit. And that is multiplied by the rapid oscillating function, which is due to the interference from the array of delta functions, or the array of point sources. Now, sometimes the slits that we are considering are so small that the diffracted field becomes practically constant over the range of angles that we're interested in. So that becomes the less interesting part of the pattern that we're looking at. And we then become more interested in the interference between the delta functions. The maxima of these interference pattern due to the delta functions is going to occur at the same place as they would for Young's double slit. However, the width of these is going to change according with the number of slits we see. So let's see how we can measure the width or even predict the width of these patterns. Let's use Fourier analysis as a tricky way to work out what the far field electric field pattern looks like for a finite grating. First of all, we'll take an infinite grating, and the spacing between those delta functions we'll call d. Mathematically, this function is called a comb function. Now, to make our grating now have a finite width, we're going to multiply it by a large aperture. So this width A is going to be the width of the grating. And you can see when we multiply those, we have over here on the right our final aperture function. To work out the Fourier transform of that, we notice that we've multiplied. So if we then take our respective Fourier transforms and convolve them, we'll work out what the Fourier transform is of our aperture function. We know that the Fourier transform of an aperture is going to be a sinc, and the Fourier transform of a comb function is also a comb function. However, the spacing between those delta functions, instead of being d, now goes as the inverse of d. When we convolve, then what we are doing is we take the sinc function and we slide it along, and every time we hit a delta function, we put in a replica of that sinc. So we slide it along another distance and we put in another sinc function. So this is our electric field in the far field here. Square that and we'll see the irradiance pattern. So instead of seeing delta functions in the far field, we now have these sinc functions, and they've got a finite width. We can consider the zeros on either side of those sinc functions to be an indicator of the width. And this sinc will have minima when the argument here, I can rewrite it here as n k sine theta d on 2 is equal to plus or minus pi plus or minus 2 pi, and so forth. If we rewrite k as 2 pi on lambda, and we solve for these first minima, what you'll find is that this width here is equal to, let's see, there'll be 2 lambda on nd. So clearly, if we increase the number of lines that the light sees in, we're going to get a smaller angle. We can then talk about what the resolution of this system will be. If we have another wavelength and the principal maximum occurs at a position that overlaps with the first minimum of the other wavelength, then we could say that those peaks are just resolved. Using that, we can find the minimum resolvable angle, which we can use to find the minimum resolvable wavelength. And with that, we can find something called the chromatic resolving power of the grating, which is defined as the wavelength of interest divided by this minimum resolvable wavelength. The resolving power, or the resolution, is given down here, down in the bottom left. The equations on the right-hand side are, if you would like to follow the mathematics through to work out the far-field electric field. So the array of delta functions gives us the electric field in the far field that's proportional to sine n, which is the number of slits, times blah, divided by the sine of blah. Now, we have principal maxima when this expression is equal to n. And if we solve for that, and we also make the substitution that k is 2 pi over wavelength, then we get the grating equation. Interestingly, this is really general. It gives the same theta locations for the maxima as Young's double slit, or regardless of the number of slits. The number of slits, as we saw, just makes a difference to the width of those spots that we see. It's really useful because we can have a grating with a known D that will be designed into the grating, and we can measure the angles at which we see bright spots, and that will tell us the wavelength of the light that's incident on the grating. It's very practical. We've also seen that the width of these spots is what defines the resolution. And the resolution is given by the ratio of the angle to the minimum resolvable angle, or the wavelength to the minimum resolvable wavelength. And that's given by the order of the diffraction by the number of lines that are illuminated. And if we're given a width of a grating of A, and we know the spacing of those lines, we can work out n, the number of lines in that grating. We run into a problem when we're using the grating to disperse light to work out its spectrum. And that's the problem of overlapping orders. So the grating equation makes it clear that m lambda at a certain angle is not necessarily unique. We could see at an angle the first order diffraction from 600 nanometer light, but at that same angle we'll also see the second order diffracted beam from 300 nanometer light, and we'll see the third order from 200 nanometer light, and so on. So the furthest apart we can see wavelengths without any overlapping is going to be given by the free spectral range. And that is given by simply wavelength over m, where lambda is the lowest wavelength that you'll be considering and m is the order. In the lab, you'll be building a grating spectrometer. A commercial spectrometer generally uses mirrors in order to focus the light or make it parallel. However, in the lab, we'll be using lenses. They're cheaper and we have lots of them. They're also a lot easier to align. But the reason that commercial spectrometers use mirrors is that mirrors can be used to bounce the beam back and forth and thereby make an instrument that is much shorter. Furthermore, they can operate over a wider spectral range. That is because they don't suffer from chromatic aberration, and also because they don't have the problem of absorption, for example, in the infrared and the ultraviolet that lenses have. In this problem, you'll look at a commercial grating. It has 500 lines per millimeter, so you can use that to work out the spacing between the lines. And it has a width of 20 millimeters. So if you illuminate that whole 20 millimeters of light, I want you to find out both the limiting wavelength resolution and also the first order diffraction angle for light that has a wavelength of 500 nanometers. We've seen this week, like last week, an example of the principle of multiple beam interference, which shows us that the more sources we have, the sharper the interference pattern. We saw that if we have two slits, we have an interference pattern that looks like a cosine, but as we increase the number of slits, then the interference pattern becomes more and more defined. Last week, we saw the same thing in the Fabry-Perot cavity. We had more and more reflections, which gave us interference between a large number of beams. I'd like you to appreciate that this is a general principle that is of great practical importance. We could look at thin film interference between a whole stack of thin films, which gives us a lot of interfering beams. What happens in that situation is we can get much sharper spectral features, as you would expect. In this example, we're looking at a mirror that's being created with 10, 18, and 27 pairs of thin films stacked together. As the number of pairs increases, you can see that the blurry spectral response of the reflectance turns into a much sharper spectral response. And the example on the right is something similar. It's actually an X-ray diffraction pattern. The axis on the bottom is related to the angle at which these reflections, which are essentially interference peaks, occur. You can see that down the bottom, where the particle size or the crystal size is very small, then we have only very few atomic planes that are reflecting. And you can see that the interference patterns are quite broad. But as the particles, in this case they're made of something called hydroxyapatite, get larger, then we have many, many more atomic planes. And that atomic planes gives us the same situation we see over here on the left, many more reflections, which gives us much more well-defined interference patterns. We can actually work backwards and use the width of these peaks to work out the number of atomic planes that contributed to that reflection. In this lecture, we've seen that diffraction is essentially a complicated case of interference. Both interference and diffraction result from the superposition of waves. We saw that Fresnel diffraction is what happens when either the source or the position of observation are close to the object that's diffracting. And although the mathematical theory to explain it is complicated, we saw a simple application of the zone plate, which is a means for focusing light that uses diffraction. When we observe much further away from the obstructing aperture, we found that we see Fraunhofer diffraction patterns. Because we are a great distance away from the object, we can consider the light waves to be plane waves. And this also allowed us to exploit Fourier analysis, because that essentially tells us that any particular complex waveform can be made by superimposing a number of harmonic waves. And using that, we were able to find the diffraction pattern by Fourier transforming the aperture. Because we are using Fourier analysis, we can also access all of the other mathematical tricks that come with it, such as the convolution theorem, which enables us to explain quite simply more complicated apertures and their diffraction patterns. We used Fourier analysis to study the diffraction grating, and we confirmed that the grating equation is given by the order times the wavelength, which is equal to the line spacing by sine theta. We saw that diffraction gratings can be used in spectrometers in order to disperse the light, and angular measurements can be converted to measurements of wavelength. We also saw that there is a limitation to the smallest wavelength that can be detected, and that is governed by the number of lines n that is illuminated.